Good morning, good evening, or good afternoon, depending on where you're joining us from today, and thanks for attending today's Cosmos DB technical training session, Table and Graph API. Before we get started today, there's a few housekeeping items that I'd like to address. If you take a look on the left-hand side of your webinar console, you should see a Q&A box. We have a few Azure Cosmos DB technical experts here who'd be happy to answer any questions you have. Above that, you should see a media player, and this is where today's screen share and demo will be displayed. If you take a look on the right-hand side of your webinar console, you should see a resource list. We've provided a few resources here that we think you may find helpful throughout this presentation. Below that, you should see a survey. We would appreciate any feedback you have on today's session to help us determine what kind of content we're going to put out in the future and to help us learn a little bit more about you. You will also receive a recording of this presentation within 24 to 48 hours at the email address you registered with. So with that, I'd like to introduce today's speaker, Luis Vasquez.
Hello, everyone, and welcome to this Azure Cosmos DB technical training series. Today, we're going to talk about specifically the table and graph API. So let's get started. Thank you, Nick. Thanks for the introduction. So my name is Luis Vasquez. I am a program manager at Azure Cosmos DB. You can follow me on GitHub, LinkedIn, or Twitter. That's where we share most of our content. And that's where you can get first-hand information on the updates with Graph API, on the updates with Cosmos DB itself. And also you can find some resources on my GitHub account, which also has pointers to the Azure samples or the Microsoft GitHub accounts with additional content for me to share to you. Today, we'll talk about two of the APIs of Azure Cosmos DB. These APIs, as you may already know, are some of the interfaces to which you can talk to Cosmos DB, and they talk in different data formats, including key value pairs. That's the specific case of the tables API, column family, as it is the case with Cassandra, documents, as it is the case with SQL API or MongoDB API, or graph, which as it is the case with the Gremlin API. I just realized that I didn't push that slide. So all these APIs are actually, you can think of them as interfaces to talk to the core values of Cosmos DB. So for every single one of the APIs, you will have all the features that include global distribution, elastic scale-out, guaranteed low latency, the 5 consistency models, and comprehensive SLAs as well. So for the APIs, how can you think of them? You can think of every specific API as an offering of its own. You can think of it as a MongoDB as a service for the MongoDB API, a Cassandra as a service, a Gremlin as a service, or tables as a service. It's also a good thing to point out would be that we also are working on additional APIs that we can share and then we can make available for in the future. And all these APIs, as you can perceive them as services of their own technologies, include all the benefits of Cosmos DB, including the aforementioned benefits. So how does this work for you? You can think of this as for the following diagram. You can think of this as if you already have an existing application for either Graph API or MongoDB or any other sort of API, you only have to change the connection string. As well, also assuming that the feature area that is covered by your application is also supported in Cosmos DB. And a change of that, and assuming that you're using any of the open source or drivers that we support, will allow you to talk to Cosmos DB. So, for example, if you have a RoboMongo application, by just connecting it to Cosmos DB, it will think that it's talking to a native MongoDB application or a native Graph or a native Cassandra application. As I mentioned, the only limitations are based on the feature supportability that we have on the Cosmos DB side. So, and that's going to be scoped to a specific version of either of the technologies that are involved, including Apache Tinkerpop, Gremlin, or MongoDB. So today, we are going to talk about specifically we're going to specifically talk about Table API and Graph API. Table API is our key value pair storage offering, and Graph API is the Gremlin API is our graph as a service storage layer. So let's start with the Table API. So Table API is a collection of key value pairs. Let me actually skip. Okay, collection API is a set of key value pairs. We only have two required properties, which is row key and partition key. Row key is a unique ID for every one of the rows, and partition key is a parameter that is used for the automatic partitioning that happens in Cosmos DB. This is the way Cosmos DB can execute horizontal scalability, and that feature is built in for all of the APIs as well. And for the Table API, for every account, you can have many collections. For every collection, you can have many rows. A collection is going to define the host to which you can connect your application to, and an account, will define the host to which you can collect your application, and the collection is going to define the specific container of all these rows that your application will be able to access. So this is a little bit of the containment model that every API will have. And again, this is shared by all the other APIs. So one of the key differences for the Azure Tables API is the fact that if you're already using the table storage SDK, the Azure Table Storage, which is a product of Azure Storage, your applications can just connect to Azure Cosmos DB Table API, and it's going to just work. The supported programming languages that we have are Java, .NET, Node.js, and Python. These are all through drivers or connectors that we support ourselves, that we develop in-house. So one thing to mention is the fact that if you are already a user of Azure Table Storage, there's two things that there's one question that will answer that, which answer will let you know if you should try out the Cosmos DB Table API, and that is, well, first of all, if you are already using table storage, and second of all, if you are being limited by the scale, I guess, constraints of table storage, right? So if you are, then Cosmos DB Table API is the solution for you. So a few of the differences is that table storage has an SLA of 2 seconds of read and writes in terms of latency, whereas Cosmos DB has an SLA of 10 millisecond read and 15 millisecond writes. In comparison, the throughput of table storage is defined as a max of 20,000 operations per second, I/O operations per second, whereas Cosmos DB Table API has no real upper limit. Since it's based on horizontal scalability, the more partitions you add, the better the throughput is going to be per operation. There's also a few differences in pricing that aren't mentioned here, but pricing, and it's related to the throughput, in Cosmos DB is based on the amount of requests per second that are allocated for each of the database accounts. In terms of global distribution, table storage provides one primary database and one read-only secondary, whereas Cosmos DB Table API provides one primary with automatic or manual failover and up to 29 additional read-only replicas. These read-only replicas, as you may know, can be distributed to any Azure region in the world. There's also a few differences in indexing, where partition key and row key are indexed in table storage, whereas there's automatic indexing on all properties of Cosmos DB Table API. Querying, you can have row scans based on a partition or row key, but every query in Cosmos DB uses or tries to use the index based on the specific case. And last but not least, the consistency parameters, consistency settings will be different based on your solution. For table storage, you have strong with primary and eventual with secondary, whereas Cosmos DB, one of its key differentiators is the fact that it has 5 different settings: strong it's a spectrum that goes from strong to eventual with a few options in between. These topics have already been talked about before. So here's a short demo on how to use the table API. This is a fairly quick, fairly basic demo. Okay, so the following is a Cosmos DB table dashboard. And if you go to the Data Explorer, you can actually see all the containment model, which is a tables account is what defines the host name of the application, the host name that the application is going to connect to. Then inside of it, we have different containers, which is our database, inner database account, if you may, which can have one or many collections. Collections are the specific tables where the entities live. Now, one quick thing to notice about Cosmos DB is that you can set the scale and settings, including indexing configurations for each of the collections. So each of the collections can have a different throughput, can have a different indexing, it can have a different time to live setting as well. So for the entities, you can actually insert or delete properties inside of the Data Explorer. And as you may see, it's just a combination of columns and keys that are stored as rows. So it is fairly intuitive to try to store data in the table storage API. And so let me start the demo. And so that's it for the tables API. Now we are going to talk about the graph API. So the graph API, graph databases are actually not a new technology. Graph databases are something that's been around for a couple years now, but they are they are a technology that has matured enough such that right now it is experiencing a boom of options, an increased amount of options in the market, as well as some media attention as of lately. So this article on Datanami actually points you to how graph databases are being used in Wall Street. They can be used for different purposes, including data analytics, including exploring different relationships in data. We'll talk a little bit more about what the best uses are for graph databases, but this is one of the biggest scenarios that are being experienced right now with graph databases. Some people have actually gone as far as calling it the year of the graph, given that a lot of vendors have been increasing their graph offerings, and there's a lot of customers that are currently exploring different ways of solving some of their data problems with graph databases. So what is a graph database? A graph database is really a flexible data model. A data model that allows you to interpret different problems, different solutions to problems in different ways. The way you can model this data is through relationships across elements, right? And so this is a great user scenario for social networks, for knowledge maps or knowledge graphs, and anything really. Anything can be solved as a graph database. There are a few graph databases in the market today. These are all the list of graph databases that are using either an open source technology such as Apache Tinkerpop, or they're using their own proprietary technologies. You can see that there's a lot of available options. I can say that a large percentage of these options actually use the Apache Tinkerpop standard that Cosmos DB uses. So if you are already developing against a TitanDB or an OrientDB, not OrientDB actually, but a TitanDB or a Janus graph, chances are that you can just switch your application through the connection string and just talk to Cosmos DB directly without having to rewrite your application. This is the list of all the graph database options in the market that are on-premise. And the following is a list of all the graph database as a service options that are there in the market. And, Cosmos DB is the first graph database solution as a service that is in general availability today in the market. So for everyone who already knows about Cosmos DB Graph API, these are the things that are new in general availability. We have improved the backend such that the Gremlin processing is now co-located with the database account, and this is all based on an Azure compute infrastructure. So there's some infrastructural changes that will improve the performance of the Gremlin processing layer, as well as the latency experience with the database accounts. We have added Python and PHP support through the open source drivers. These are maintained by the Apache Tinkerpop framework, as well as some members in the open source community. We have a private preview of a bulk import library. This is a C# library that can be integrated with an application such that you can insert in a bulk fashion in nodes and edges, vertices and edges at a graph database account. Okay. So let's dive a little deeper into what a Tinkerpop graph is. So Tinkerpop is what's called a property graph. Property graph is centered around the relationships that you can create in data, as well as the properties you can store in either their relationships or the vertices. So a few keywords to note here is that vertices represent entities, whereas edges represent relationships. This is just the slang that is used inside of the Apache Tinkerpop graph database database environment, graph database ecosystem. And these two types of objects both can have a list, an arbitrary list of key value pairs that can include strings, booleans, numbers, etc. And we chose this standard because this is a standard that is used by most graph database vendors. Neo4j has its own standard, but a lot of the open source on-premise graph databases have used and have implemented a sort of Gremlin support as well. So for example, a vertex can represent an element or an object inside of a graph. And in this case, I'm representing a vertex Luis with an ID Luis. It has a label. A label is a special property that just denotes the type of object that you are representing. So label, in this case, is person. And a list of properties, for example, age 25, is just some of the data that you can insert into this object. Then the edge represents a relationship between two objects. So for example, an ID of the edge is also a unique value that Cosmos DB automatically fills, and that's the same case for the vertices. The label could represent a relationship, a type of relationship. So in this case, this example shows the works at relationship. This is meant to connect to another vertex. That's the place where Luis works at. And a list of properties include additional information like my role, which is a program manager. So a basic graph would look the following way. So you have three vertices, and for example, we have the vertex Luis, which is a type of person. It's of age 25 and likes tacos, just the arbitrary properties that can be inserted into this object. And the edge, there's an edge that points to works at, the one on the left, and it just points to an object of type Microsoft, an object of ID Microsoft with a label company, right? This label denotes that it can be a different entity than the one that we have first defined, and some additional properties as well. Or you can use this to represent, I guess, human relationships. For example, there's an edge to the right that says is married to, and just for example, I don't know, Emma Watson, which is a vertex of type person. Properties include is famous, true, and likes tacos as well. So this represents a very basic graph structure and a very basic explanation of all the properties, all the types of objects you can model with the graph database. So when do you need a graph database? One of the main things that a graph database solves is a relationship-heavy schema. So for example, if you're coming from a relational database world, you might feel like eventually the data modeling of normalized relational tables can only be so readable until at some point, So think about a level 3 normalized database where you have tables that denote relationships, that denote other relationships as well, that end up having the information stored in a table that requires a couple joins to get there. And relational databases are really not optimized for joining tables of different ways. Like that is one of the main operations, but if your queries experience more than 3 joins for every single operation, for every type of average query that you execute, you might actually have to explore a different kind of solution. Another symptom where you might need a graph database is if your relational queries are complex. So for example, if 90% of your relational queries require at least a couple of joins, then the performance or the expected readability, the readability or the programmability layer for your application could be improved by a graph database. This relates directly back to the other to the previous point of a normalized database having some of these issues. And the real problem is really experienced when you have to maintain or upgrade or change this database. For example, if you have a change of requirements such that you have to add additional entities or additional properties, it will be much easier to make those changes, which are really business changes, business logic changes, in a graph database than it would be on a completely spread relational model. And this ties to this next point, which is when do you need flexibility when modeling your data solution? So a relational table might find a case where your data could not fit the specific row or the specific event that you're trying to insert into it. So a graph database solves that problem. I've already explained this part where this flexibility in modeling can actually enable your response to additional business requirements. So in diving a little deeper into this technology, the Graph API uses the Gremlin language, which is a very easy to learn functional language that is shared across many other database vendors. So the Gremlin language uses a set of steps or functions, these both are the same thing, to execute operations on a concatenated set of results. So for example, if you have an operation and you follow it with an additional function, this function is going to affect the result set provided by the first application, by the first operation. And this is a Turing-complete language that allows support for create, read, update, and delete operations as well. So this is a very easy example of how the Gremlin language works. So g.v is a query, it's a selector that would return one vertex of a certain property that is specified as a parameter. Then this is going to, and in this example, this is going to return the Thomas vertex here. And then the next operation, out E, is going to be executed on that first result set that function returned. So that function returned the first vertex, which was Thomas, and then out E is an operation to select the edges that are coming out of that vertex, and selects them, and these edges are of the type nose. So it's a relationship of type nose that is being selected right now. InV is going to select the vertices that operation points to. So if you read this query from left to right now, it says select Thomas, then get all the relationships of type nose that Thomas has, and then get the objects that those relationships point to. And at the very end, it just selects the first name of both of the objects that are pointed by this relationship. Here's a more complicated kind of graph. So the first part will select all the vertices. G.v, in that case, will return all the set of the vertices. Then it would filter them by the types of vertices that are people or persons. Then after that, and we are actually on the first row of the query, and after that, it will select those that have the name Thomas, the first name Thomas. Then after that, it will select the outer edge of type nose and the in-vertex kind of pointing to the relationships that are being pointed by the type of relationship knows. Then it's going to select from those results the vertices of type people or persons. Then it will get those relationships of type knows from those people that are known by Thomas. And then at the end, it will just filter the people, the value person of those vertices, and then it will just return the first name. So a brief explanation of this query is get all the people that are in this graph. Get all the objects in this graph. Select the people in this graph. Select a specific one that's called Thomas. Then get the relationships from that to other people, and then get the second level relationships to other people. So this query returns people that are known by people that are known by Thomas. So friends of Thomas, if you may. And this is another example of the complexity of queries, or the complexity of exploration of relationships that this technology can allow you to explore. So here's a demo of how to use a graph database to solve a real problem, per se. So what I call this, and this is going to be available on GitHub for you to use as well, is a busy traveler problem using Azure Cosmos DB Graph API. So in order for this to be really real world, I chose a real example of an airport, actually a pretty terrible airport. This is LAX, and the LAX airport is known for not being easy to go from one point to another. For example, all the terminals are in the counterclockwise order, so you may see that it starts with 8 and ends with 1 in a counterclockwise perspective. The numbering system is a little confusing. You have 1, 2, 3, then terminal B, then 4, 5, 6, 7, 8. There is no way to go from terminal to terminal inside of the airport without having to exit the terminals and then, run around, basically. And then this is actually common in most airports, but from arrivals to departures, you have to change a level, just adding to the complexity. So the way you would model this problem with a graph database is by creating a vertex for every single one of the terminals, and then relationships that go from a terminal to another. So I actually used only one arrow here, but this means that there's a bidirectional relationship, just two edges, one of them that says go to the next terminal, one of them that says go to the previous terminal. And there is no connection between terminal 1 and 8, just because in the real world there isn't a way other than just taking a shuttle from here to there. But inside of the airport, and this is where the problem statement comes. Inside of the airport, you find yourself a combination of gates and restaurants. And this is how I modeled this problem right now. If you can connect externally from one terminal to another, you can actually connect internally from one gate to another, or from the terminal to any given gate, as well as the connections from the terminal to any given restaurant, and from gates to restaurants back and forth. So this is a set of connections that will describe how you can navigate inside and outside of the insides of a terminal and the outside, which is the airport, between terminals. So for this, one of the most common problems, or at least that's one of the problems that I experience when I fly, is that you have to get from a given gate A, like for example gate 1, to a target gate B, gate 4 in this example. But there's a limited amount of time. There's a constraint on the time that you have to go from one gate to another. But as well, you might as well just also pick up some food on the way. And this is something we've added to the problem such that it is a little bit more complex for it to be explored as a graph database solution. And so from one gate to another, you'd have to traverse through different ways, and there's obviously certain most optimal paths you can take. So let me share my screen so I can show you how this is set up in Cosmos DB. Okay. So this is the graph that I was telling you about. The graph is a set of vertices of type terminal, gate, or restaurant, and they have the name, an iteration of the name terminal 1, 2, 3, as well as an ID that relates to its type and relates to the number of terminal it is pointing to. And inside of it, we have, let me actually expand this. And inside of it, we have a set of connections for the gates. So for example, from a given terminal, you can get to either of the restaurants in Terminal 1, including Chipotle, McDonald's, Wendy's, or either of the gates, as well as to the next terminal, which is Terminal 2. Let me actually expand this. This is the Data Explorer. Just a quick note on the Data Explorer. If you have a graph account, the Data Explorer will turn into this Graph Explorer that allows you to visually explore the data that you have inserted in the graph database. This Graph Explorer is optimized for quick visualizations as well as demos, but if you need a more robust graph visualizer, we recommend different applications, including the Graph Explorer, which is, I think, it's linked to this webinar as well. But in any case, this is the Graph Explorer, and in order for you to get from one terminal to another, you can execute a query that selects a type of terminal. So g.v.t1 will select a terminal, and then once you can select a relationship that goes from a specific terminal to another. And I have an application that's written for this purpose, but I'm just going to show you a little bit about how the queries work by themselves. So you can explore the edges here as well. So once we select the terminal one, you can see that, let me show you the targets. You can see that it has relationships that target other objects. And the target to gate will get you to either one of the gates. So for example, if you wanted to get from the terminal one to the gate one, you use the to gate out relationship. And this will return you all the gates that you can get to from the terminal. Then, if you want to filter these gates, you can have a filter that's the ID, and then you can select G1. And so this selects the gate G1. This is actually the only result that is returned by the Graph Explorer. And you can explore how this is internally represented as a JSON object. So this is a basic case for a graph database. Let me show you how you can actually write an application for it. And so this application is written using the Gremlin.net driver. And this Gremlin driver actually asks you, this is a very simple application that will also be available in my GitHub repository for you to try and use as well. And in this application, you get three inputs. One of it is the origin gate, the other one is the rating of the restaurant that you want to stop by, and the other one is the target gate. And through those, we form different queries. This is actually demo code, so excuse the comments. In these queries, you can actually pass in those parameters, and there's really two cases. If you stop at a restaurant in your same terminal, or if you stop at a restaurant in your second terminal. So this separates these cases and shows you how to create queries for those two cases. So let me start the application. Okay, so the application will ask you, which gate did you arrive to? Let's just say gate 3. And we're going to gate 5. And this question will filter all the restaurants you can stop by. So how picky are you feeling today? Well, it's a Tuesday, so I'm 0.4. We'll settle with anything. And these are the results that you get. So this is the query that was generated and then executed against the graph database. And the result says, you land in gate 3, go to Chipotle, pretty good option if you ask me. Then exit through terminal 1, change to terminal 2, and then go to terminal 5. This is for the case if you visit a restaurant in the same terminal. If you visit a restaurant in another terminal, this query was generated, and the result is the following. You land at gate 3, exit the terminal, go to the next terminal, go to Smith & Wollensky. I'm not even sure if LAX would have that, but anyway. And then go to gate 5. So this query actually makes use of a repeat step, which loops a set of functions or a set of steps before it can get a condition that breaks that loop. And this also makes use of a hash filter for both edges and vertices. And here are some of the functions you can pass in, like which is for example this one, that is a greater than function to change this to compare this numerical value inside of the properties of one of the objects. And then at the very end, you have a path which will return you all the vertices that were visited with this traversal. In the Gremlin language, the queries are called traversals, for example, traversals. And then by name, we'll just return you the name properties of all these objects. So you can do a quick calculation. So if we go back to the slide deck, you'll see that there's a cost associated that is stored in each of the relationships, and this cost is expressed in minutes. So this query now selects all of the edges and then sums the minutes that it takes for every option. So you may see that in this case, this option number 1, which if we remember is like land at the gate, stop at Chipotle, switch terminals, and then go to your destination gate, will only take 28 minutes. Whereas if you go to a different terminal, it'll take 33 minutes for you to complete this process. So as you may see, as exemplified by this demo, that this is an automatic way of traversing different objects and then making some additional calculations on it, on like which path took me the longest, which path which are the set of paths that have the options that I'm looking for, et cetera, et cetera. And that is what that is one of the things that the Gremlin language can actually solve in an easy to read kind of format. Okay. So going back to the slide deck, let me see. So as you may see, that is the way that the application represented these airport constraints. There's as I mentioned, there's a cost associated to every one of the vertices as well as every one of the restaurants. There is a money cost, a time cost of switching terminals, et cetera, et cetera. So here's an explanation again of all the queries that were run against it. So start at G1, start from the gate that you arrived at, then pick a restaurant that has a rating of at least 0.3 stars, or 0.3 or 3 stars, and then go out to switch terminals, then go to your gate and return the path by all the names. This is an explanation of a step-by-step query that you just saw before. And then this is the second case in which you switch the terminals first, and you stop at a restaurant to get to your gate. So you start at the gate, you go to the next terminal, then you go to restaurant that is filtered with at least 0.8, which would be 8 stars here. Then return to the terminal and then go to gate 4 and get the entire path. So this is an explanation of how Graph Database can solve a couple of problems that are experienced with data modeling. So you'll see that the flexibility in this case is very it provides a lot of capabilities that allow you to be flexible about how this problem works. A way to expand this problem would be if a new terminal is built, or if you want to represent parking lots, you can add those as vertices as well that connect in a certain way to the terminals, or you can add restaurants that are outside of the airport as well. One other quick way to expand this problem area would be by adding restrooms inside of the restaurant, and inside of it could be the restaurants or the terminals, and that way you can make a more complex calculation that can be presented in an application. And this one of the features of Cosmos DB is that this can be a globally distributed application. This has also the guaranteed SLAs, which is financially backed SLAs. What that means is that there will be a financial retribution if we ever fail to achieve these SLAs. So all of these properties, all of these features can be accessed through an application of this kind. And a good way to get started on this would be to try Cosmos DB for free. If you go to aka.ms try-cosmosdb, you can actually create an account of your choice and use it. I think it's a time-bounded use for the account, and so you can manage all your testing against every specific account without any cost associated with it. And you can create a SQL account, a MongoDB account, a table account, as we explained before, or a graph database account. So this is the presentation, and you can access some of the resources. In the resource list, you'll find a Create a New Table API database account, and a frequently asked questions. This second link is very useful if you're an existing user of the Azure Table Storage solution, and it'll answer questions like, when should I use the Azure Cosmos DB Table API? As well as get started with the Gremlin Graph API and the Gremlin console. The Gremlin console is one of the open source applications that are made to learn about graph database, and it can connect to remote databases. So that is how we use the Gremlin console in Cosmos DB. Through every one of these tutorials, you will be walked through a set of steps on how to create a database account, as well as downloading the application and connecting to the database. These tutorials are all self-contained, so you don't need any requirements previous to the tutorial. And if you do, it'll be things like the runtime that you have to install or the libraries that you have to install and how to set that up as well. Those instructions will be included in the tutorial. There's also an introductory page on Graph API with more examples on how to use Graph API to solve some of the problems that you might be encountering, some of the data problems that you might want to try it out against, as well as the Gremlin support. So this is a list of all the functions that are supported by Cosmos DB in the Gremlin language specification. So yeah, I think we'll be open now for Q&A session.
All right, thank you, Luis, so much for that great presentation. So as I mentioned earlier, if you take a look on the right-hand side of your console, we do have a couple of resources. Feel free to download and click on those if you'd like. And then below that, there's a survey that I mentioned earlier. Please, if you have a moment, fill that out just to let us know a little bit more about you and let us know how we did today. So we still have a few more minutes before we reach the end of our 60-minute time limit. So we would like to now open it up to any questions that you guys have. So if you have any remaining questions, please feel free to pop that into the Q&A box, and we will address those as they come in. So again, Q&A box is open. Feel free to pop anything in, and we'll answer it.
Okay, I'll pick some of the questions that are in the Q&A and answer it live.
Yeah.
Okay. Cool. So one of the questions is it possible to migrate an existing Azure storage table storage into Cosmos DB Table API? Yes. As we mentioned, the drivers that are compatible with table storage are also compatible with Cosmos DB Table API. So this would require just creating an account and then switching the connection string. We recommend updating to the latest drivers, the ones that we are providing, but the Table API ones, if you're trying to do some quick, bless you. So if you're trying to do some quick proof of concept kind of work, you can just change the connection string and it should work like that. Kindly share the link of the sample application. Is it available in GitHub? It will be available. I just need to clean up some of the application, make it presentable for the open source community. So I will share that as well. If you follow me on Twitter or GitHub, Twitter is _LBOSQ, and GitHub is my name, LUISBOSQUEZ, Luis Vasquez. That's where most of the resources that I'm using will be available. Has anyone migrated from RDBMS to Graph Database? Well, one of the customers we've spoken about is Skype. Skype actually uses our Graph Database as part of the friend suggestion feature, and that used to be hosted on a relational database. So yes, there are some cases. Since Graph Database is a really flexible data model, it is really hard to prescribe a single solution, a single way in which a Graph Database can solve a relational database problem. But it is definitely it is flexible enough such that you can try, and we have seen people perceive additional benefits in terms of scalability, in terms of flexibility with the Gremlin API. Okay, let's see. Are there any reservations in regards to view control and security when using Gremlin? So some of the Gremlin features include, not on the Gremlin features, sorry, the Cosmos DB features include the fact that you can use a primary or read-only keys, so read-write or read-only keys against the database, and this is obviously also available for the Graph API solution as well. There's also additional features including IP address whitelisting, so you can close the endpoint to only a few set of allowed IP addresses. This is a feature that is available for all sorts of APIs in Cosmos DB, and Graph API has it as well. This is a good question, can I call the Graph API against an existing MongoDB document store, or do I need to run a parallel DB? So for today, you'd have to run separate accounts for separate APIs. So for example, when you create an account, your API choice will be one of the first things you do, and that cannot change after you create the account. Please email us if you have a case where you need to have an existing Graph or SQL API or MongoDB API with a Graph API, say, layer on top of it. How to use Graph in .NET Core 2.0. What we recommend is the open source driver called Gremlin.net, and Gremlin.net is actually available freely to be installed, part of a contribution by the community, and supported and maintained by the Apache Tinkerpop community. So that is .NET Core compliant, and it's compatible with it. You only have to install, I think one of the specifics of that is you have to install it using the NuGet client, CLI client, and that, and then it's just as easy as installing NuGet install Gremlin.net, and the specific version that works against Cosmos DB is 3.2.7, because that's the Apache Tinkerpop version that we support. Is there a walkthrough tutorial that shows the demo that was done today? Again, this will be available in my GitHub account, so make sure to follow me at Luis Bosques, which is a single word, on GitHub, or if you follow me on Twitter, I will announce the links where it's going to be available. How can someone start learning the Gremlin language? If you go to the Apache Tinkerpop website, that could have been a good resource. Let me actually reply to all with that answer. There is a pretty good set of documents that's called the 1, 2, 3 of Gremlin, and that's a pretty good resource to start with. It's called the first 5 minutes of Gremlin, and that will teach you all about the Gremlin language as well. Let me send to all, so you should all see this answer. Okay, so there's another question. This is more about SQL API, formerly known as document DB. And it says, does that mean that we cannot have joins in separate documents? So two things. First of all, I was comparing Graph database against a relational database. And as you may know, SQL API from Cosmos DB is not a relational database. It's a document store. That said, you cannot have joins for two separate collections. Per se, it doesn't work like the joins in a relational table where you join two sets of data using the joins function. But joins in SQL API, formerly known as document DB, work as an inner join. So it joins information such that it can be presented in a different way by the query. Here's another question that's, hi, can Cosmos DB, Graph API, and SQL API, aka Document DB, yes, share data? The answer is yes. Once you create a Graph API account, you have both endpoints for the SQL API and the Graph drivers. However, it's very easy to corrupt your data if you don't know the exact format. So what you can see is the way the JSON is stored in the backend, and that will give you a good indication on how to use SQL API and Graph API with the same data set. How does Gremlin fare in terms of performance? So it is optimized for joins, and it really depends on how you set up your partitioning, how you set up your request units per second. A short answer would be Gremlin is optimized for obtaining relationships and deeper levels of relationships, not as not as much as it is for aggregations, for example. So it really is a tool that's used for very specific for these specific purposes, and that's how it can be best taken advantage of. Someone said, "That's a lie. Emma Watson is married to me." And like, well, fine. I don't know what to say. She didn't tell me anything. Okay, there's any more questions you might find interesting? Can you put the GitHub or Twitter for us slow typers? Sure. So Twitter, where I'll be sharing announcements for the demo content for Cosmos DB, is the following. And GitHub, you can go to Azure Samples or Microsoft, or my GitHub, which is Luis Bosques. I'm going to share this to all the attendees. How similar is Gremlin to Neo4j? Great question. Neo4j uses a completely different language, which is called Cypher. And Cypher is not a functional language. It's a type of a script that needs to be compiled and then executed. And it does some interesting things too. Cypher can do some data transformation as well. Cypher, you can see it as very similar to the SQL or T-SQL query language. Whereas Gremlin is a more of a functional, append to the previous results that kind of language. In terms comparing Graph API against Neo4j isn't really it's two different categories, because Graph API is actually a hosted managed graph database, whereas Neo4j has offerings for on-premise mostly. So I think those are some of the differences you can perceive. Okay, I think I answered this as well. How the consistency levels work for between strong and eventual for graph? I see. Okay, so consistency levels. This was probably discussed in the first session, but Cosmos DB has replicas inside of every database account, right? And so in reality, to see the differences between the consistency models, they are most noticeable when you have a globally distributed application. So if you have an application that shares data between, I guess, China and the United States, East US, that's where eventual and strong will see some noticeable differences. However, and these differences are the same between Graph API, between SQL API, and so on and so forth. Cosmos DB shares a storage backend that allows these that translate these queries between the Gremlin queries and the Cosmos DB queries. So what are my options if I would like to expose interactive graph visualizations? The Data Explorer is one of the options. There are some third-party vendors that actually provide different solutions. So part of the reason why we chose the Apache Tinkerpop standard was because it provided a huge ecosystem of solutions that can be leveraged and connected to Cosmos DB because they are Gremlin compatible. So there are a few options out there. We also have an in-house application that's called the Graph Explorer, which is a .NET application that can be extended, and it has been, we have had some users contribute back to it. So, so almost like our own open source application that has that behavior. Let me actually send a link to that application as well. So this see. So if you go to Azure Samples and go to Graph Explorer, that's where you will see that's where you will see the Graph Explorer application. Okay.
All right, so it looks like we have reached the end of our 60-minute time limit. We'd really like to thank everyone who joined us today. And if you're interested in learning more, we do have a session next Tuesday on building MongoDB apps with Azure Cosmos DB. So again, we'd like to thank everyone for joining us today, and have a great day.